rule for derivatives, right? You have a product. A product of derivatives. You're taking the derivative of the product. What do you get? 1D.
F prime x plus f times gx plus fx times g prime x.
Exactly, right? F prime x times g of x plus f of x g prime x. Right? There's the quotient rule. Right? What's the quotient rule? Somebody other than Wang Di. Wang Andong, do you want to tell us the product rule? Do you want to tell me the product rule? No, you don't want to. It's okay. You don't have to. Somebody else. How about you, Li Xiao?
No idea.
No idea? Okay. Okay. Does anyone know the product rule? I mean, so the quotient rule. So maybe you don't know the name. You have a division of functions, right? Thank you. Thank you. What's your name again? Thank you, Chen Yuanhao. Yeah, don't talk too fast. I can't understand. Yeah. Okay. Yeah, the quotient rule, right? This is the quotient rule. Bottom function times the derivative of the top, minus the top function times the derivative of the bottom over the bottom squared, right? And then there's this thing called the chain rule, which talks about the composition of functions, right? Right. What is it? Chen Yuanhao, how about you tell me? Mm-hmm. Exactly. F prime gx times g prime x. Right? Right. So, for example, right, if I have the derivative of, say, the sine of x squared, right, then everybody write down the answer to this. Take 10 seconds and write down the answer. What is this? Okay, turn to somebody next to you and say, this is the answer. Turn to somebody nearby and say, this is the answer. You two talk to each other. Talk to each other. Talk to somebody nearby. Say, this is the answer. Wang Di, talk to this. I'm sorry, I forgot your name. Okay, so what's the answer? Who would like to tell me what the answer is? Who would like to tell me what the answer is? I'm going to choose Jin Xiaojing. Who is Jin Xiaojing? Oh, that's you. Okay, what's... You don't know? Okay, that's all right. I'm going to choose somebody else. Me Payton.
X time.
Right, you have a composition of functions, right? You've got sine, and then you have x squared. right? So you take the derivative of the sine. What's the derivative of sine? Cosine. Right? Cosine. And you evaluate that at x squared. Okay. And then you multiply it by g prime. So that's 2x, right? Okay. So the chain rule.
Time.
That's it. That's it. That's the end. That's the end. Right? You just take this guy times the derivative of this evaluated at here times the derivative of the inside guy. Right. So right. So for example, if I had the derivative of sine x squared, then what would that be? Again, take 10 seconds and write down the answer. Don't say it, don't say it, don't say it. Okay, talk to somebody nearby. Okay, would somebody like to say the answer? Who would like to tell me the answer? Anybody? Except for you, Bumpy. You're not allowed to talk. Yes. What's your name, please?
Chen Xiangyu.
Shang Xiang. Okay.
2 sine x times cosine x.
Yes, 2 sine x cosine x, right? The derivative of sine x quantity squared, right? Because here, right, your function, your outside function is the squaring function, and your inside function is the sine function, right? This is f of g of x, right? It's the square of g of x, right? The square of sine of x, right? So you take the derivative of that, right? You take so you take f prime evaluated at g of x, oops, times g prime x, right? So that's going to be 2x evaluated at sine of x, so you get 2 sine x, and then times g prime x. G prime x is cosine x. Right? Okay, so that's the chain rule, right? Okay. Any questions on that? Okay. So those are some basic rules of differentiation, right? Basic rules of differentiation. Here is, I think, one of the most important theorems in differential calculus, the mean value theorem. Okay. So really the most important theorem. In differential calculus. Can anyone tell me what the mean value theorem tells you? Anyone know the mean value theorem? Yes, I'm sorry, I forgot your name again. Chen Yuanhao, yes. Go ahead.
If f is continuous at the interval kb,
Mm-hmm.
and is differentiable on AB, then there is a C, and f prime C equals fa minus f A minus B.
Great, perfect. Great, exactly. Right. So, great. So, oh, by the way, this backwards E means there exists this ST means such that. So the picture is like this, right? You have some function on AB, and it's continuous. Sorry, this says continuous. It's continuous on AB. It's differentiable on the open interval AB. Then there's a point where the slope of the tangent line equals the slope of the line through the endpoints. Okay, right? This is the, let me write it, people usually write it the other way. It's the same thing. F of B minus F of A over B minus A. Right, so this is F of A, this is F of B, right? This distance is F of B minus F of A, this distance is B minus A, right? And so this thing is the, if I make a line through here, right, this is the slope of this line. Slope of this line, right? So it says that there's some point where the slope of the tangent line, there's some point C where the slope of the tangent line is the same as the slope of the line through the endpoints. Okay. There is a point, so there exists a point in AB where the slope of the tangent line equals the slope of the line through the endpoints. Endpoints. Okay. There is a point where the slope of the there's a point where the slope of the tangent line equals the slope of the line through the endpoints, right? So if I have something like this, right? Here's the line through the endpoints, and you see that there's one place where the slope of that guy equals the slope of this thing. Right? The slope of the tangent line equals the slope of this line through the endpoints. The mean value theorem. Okay. Most important theorem in differential calculus. Okay. Does anyone have questions on what this means? What this means? Any questions? If you're thinking about if F is position, like in physics, if you're thinking about physics, if F is position, then what's this? If F is position and this is a time interval, right? What is this? This is the change in the position over the change in time, right? Change in position over change in time. So that's the average speed, right? The average speed. And this thing, the derivative is, of course, the instantaneous speed, right? So what it's saying is that over any time interval, there's a place where the average speed, there's a place where the instantaneous speed equals the average speed over that time interval. Okay. That's what it says, in terms of physics. Okay. So, at some point, the instantaneous velocity equals the average velocity. Physically. Okay. 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 Other things. The notion of the antiderivative. Right. What's an antiderivative? Right. F. We say F is an antiderivative of little f if what happens? What does it mean? This guy's an antiderivative means that it's too easy. If you take its derivative, right, if f prime equals f, right, it's the antiderivative. So for example, x squared is an antiderivative of 2x. Right, because the derivative of x squared is 2x. X squared plus 1 is also an antiderivative of 2x. Right. X squared plus 2 is also x squared plus anything, x squared plus c for any c in the real numbers. Is also. Okay, and actually there's a theorem that says that if f and g are both antiderivatives of the same function, then f minus g is a constant. Is constant. Right? They have to differ. They have to differ by a constant. Right? Right. The difference. If these two functions have the same slope at every point in time, right? If they have the same slope at every point in time, then their difference must be constant. Right? Their difference must be constant. And this actually comes from the mean value theorem. Right. Okay. What else? What else? There's this thing called the indefinite integral, right? Indefinite integral. Indefinite integral. When we write something like this, what we mean is that this is the This is all antiderivatives of little f. Right? So for example, if I write f of x dx, well, that's going to be x squared over 2 plus c. Right? Right. These are all the antiderivatives of x. Right? When I write something like this, what I mean is that this is the collection of all antiderivatives of this function. Right. So this is the same thing as saying that x squared plus c are all antiderivatives of x. That's what this notation means. Okay. Okay. That's the indefinite integral, and we also have this thing called the definite integral. The definite integral, right? You have this thing. You have a function on AB. You have this function on AB, and you define this thing, the definite integral. Can anyone explain? This is kind of a hard one, but can anyone tell me what the definite integral is? The area. Okay, so it's the area. Area. Right. Does anyone have another way of talking about it? Did anyone see this term Riemann sums? Riemann sums? Anyone seen this term? Or like, right? So how do you get the area? Well, the way to do it is you divide the base into you partition the base, and then you take sample points, right? You take some sample point, you take the height there, and then you multiply by the width of the base, right? You take a sample point, height there, and multiply by the width of the base. Basically, you take a bunch of rectangles, right? You take a bunch of rectangles that approximate the area, and then you add them together, and then you take the limit as the partition becomes finer and finer. Right? Has anyone seen this? Has anyone seen this? No? Yes? Okay, good. Good. You should. I hope you've seen it. Right? So it's actually the limit of Riemann sums approximating the area. Right? The limit of summation f x I star delta x. I equals 1 to n, as n goes to infinity. Right, this sort of thing, where these are sample points, the width of something. Right. So to find a definite integral, usually you have to go through a painful process of making all these rectangles and then let them become finer and finer and finer. Right? It's very annoying. Right? It's tedious. It's a pain, right? Pain. Right. It's a pain to do. Okay. But fortunately, one has the fundamental theorem of calculus. Fundamental theorem of calculus. Oops, calculus. Right, that says this, right? If f is continuous on AB, then the definite integral equals something, right? What's the fundamental theorem of calculus? Can anyone tell me the fundamental theorem of calculus? I hope you're just being shy. Does anyone know the fundamental theorem of calculus? Close your eyes for a second. Close your eyes for a second. Okay. Raise a hand if you have not seen the fundamental theorem of calculus before. Oh, okay. Okay. Some of you have not seen the fundamental theorem of calculus. Okay. All right. Who? Okay. And, open your eyes, please. Okay. Good. Okay. Then I know where to start teaching. Okay. So okay. So let's talk about it. Okay. So right. So there's this thing called the definite integral, right? Maybe I should ask you again. Close your eyes again. Raise a hand if you've not seen the notion of definite integral. Okay, open your eyes, please. Open your eyes, please. Okay. So almost all of you have seen the notion of definite integral. Those of you who haven't seen it, just think of it like this, right? When we're talking about the definite integral, what we mean is that we're talking about the area under the graph. Okay. So we're talking about the area. You have some function. You have some function, and what this basically means is the area under the graph. Okay. So the area under the graph, but it actually means it's a little bit more complicated than that, because it means the signed area. The signed area under the graph. So if you have a graph like this, then we get a negative number, right? So this will be a negative area. Okay. Is it time to stop? I don't think so. Okay. 12 o'clock. Okay. So you get this signed area, and like I said, the way that you actually figure out the area is by approximating, using rectangles, right? So first you take a very simple approximation. You say, okay, I'm going to split the base into 3 parts. And then I'm going to choose some points in those intervals. I'm going to evaluate the function at those intervals, and then I'm going to multiply. Right? I'm going to take x1, x2, and x3, and I'm going to take f of x1 times b minus a over 3, and I'm going to add that to f of x2 times b minus a over 3, plus f of x3 times b minus a over 3, right? Where this length here is, this width here is b minus a over 3, right? It's the length of this interval, right? And so you take the height and you multiply, and what you get is the sum of these areas here, like this, right? You get the sum of these areas, and then this approximates the area. It approximates the area, right? Right, and then let the partition become infinitely fine. Okay. Infinitely fine, right? So you, the second time you divide it into four parts, and you do the same thing. You do it 5 times, divide it into five subintervals, and you keep on going like that, right? And in the limit, you get the definite integral. Okay. In the limit, you get the definite integral. Anyway, come and those of you who haven't seen it, then just come and see me. So let's start from here. Okay, let's start from here. This is really the beginning of the course, because some of you haven't seen this already, and this is important. Okay, so the second fundamental theorem of calculus says that you don't have to do that, right? Says that you can avoid doing this limiting process if your function has an antiderivative. Okay, so if f is continuous on AB and big F is an antiderivative of little f on AB, then the definite integral is just going to be f of b minus big F of b minus big F of a. Okay, so this should be sort of like, the way you want to think of this is like a miracle. A miracle, right? Because without this theorem, if you don't have this theorem, then the way that you find areas is very, very tedious, right? You have to take these approximations, and then you have to take finer approximations, and you have to let them become infinitely fine, and then you get this number coming out of it, right? But that's very hard to do. Okay, but here it says that you don't have to do that. All you need to do is find an antiderivative, and then evaluate it, right? So, for example, if somebody says, here is the sine function, right? Here is the sine function, right? F of x equals sine x. Okay, and they say, what's the area here? Okay, what's the area? Somebody tell me what the area is. No, don't tell me what the area is. Figure out what the area is. Take 30 seconds and figure out the area. What is this area? Okay, talk to somebody nearby and tell them what your answer is. Okay, would somebody like to tell me what the area is? What is the area? 2, right? 2. Did everyone get 2? So I hope none of you did it by using Riemann sums to approximate, right? Did anyone? I'm just joking. Nobody would do that. Right? So, but without this theorem, the way you would do it is to chop this up into 2 pieces, into 3 pieces, into 4 pieces, into 5 pieces, and approximate them with rectangles, and then keep on going from there, right? It would be a pain, but in the end, you would get 2. You would also get 2. Okay. Of course, the way you did it, Chen Yuan, how do you do it?
So the integral of sine is you get is cosine negative cosine.